material. Steel has a lot of those, and hence, just give me a moment. Just let me ensure that the recording is started. Yeah, thank you for starting it, whoever did it. Yeah, so it matches a lot of our requirements, as a construction material, and therefore we are using steel. Now let us compare it with its peers and try to understand why should we choose and in what situations should we choose steel over other materials. Okay, so I've sort of categorized into three. First is that what are the intrinsic properties of steel? What does it have inherently in it as a material? And then what properties does give steel an edge over the other commonly used construction material, which is reinforced concrete. And I think we have already looked at the opportunities that steel provides for architectural expression by looking at numerous examples in various categories. So the first property is it has a very high strength. It has a very high strength per unit weight. Now, to sort of understand this, just imagine that Tanay has got a very good build, and his weight is say 60 kgs, and when he's working out in the gym, he can for biceps he can lift 20 kgs with each arm. Okay, so he has a certain weight, and there's a certain weight he can lift. I, on the other hand, am not as fit as Tanay. I have a weight of say 75 kgs, and while I'm working out, the maximum weight that I can lift while doing biceps is say 10 kgs. So there's this difference between my strength and the weight that I can lift, and Tanai's strength and the weight that Tanai can lift. So it is no brainer that Tanay has a better physique. He is better equipped for physical challenges, and he has a better strength to weight ratio. Okay. Similarly, uh, let's go back to the presentation. Steel has a better strength per unit weight. Okay. So before we get into what it means, let us just try to understand what are the different types of steel and what does the numbers mean with regards to its strength. So very generically, steels are classified as standard structural steel. It's also called as mild steel, and then high strength steel. Now look at the designation here. The designation says Fe 410. I'm sure that everyone of us know that Fe stands for iron, and this is how steel is abbreviated. That Fe 410. 410 is the ultimate tensile strength. It is the highest point on the curve. So it is the ultimate tensile strength, and then the yield strength is some portion of the ultimate tensile strength. So this number signifies what is the ultimate tensile strength. Moving on to the high strength steels, we have Fe 440 with a UTS of 440, then 540 which is 540, 490, 490, and so on. Okay. The objective is not to remember these numbers. The objective is to understand what Fe 410 mean. Okay. And everything, so 410 is the ultimate tensile strength in megapascals. And megapascals is nothing but Newton per mm square. So, one of the challenges that I face in this course is, getting you comfortable with the units. Okay, everything has a unit, it has some meaning. So, it's best to, when you mention a value, the best thing that we can do is always mention a unit with that. So 410 megapascals or 410 Newton per mm square. These are the different grades of steel. Now, ABC stands, ABC stands for, it is a function of the application of the steel. We're not going to get into that. So, all we have to remember is what is this number. Perfect. Now let's get into strength per unit weight. Now let us just take an example when we are comparing steel with concrete. Let us say we are considering mild steel that has a yield strength of 250 megapascals. And let us consider the commonly used reinforced concrete grade, which is 40 megapascals. M40, heard of it, right? Now, steel has a density of 78.5 kilonewton per meter cube. On the other hand, reinforced concrete has a density of around 25 kilonewton per meter cube. So if I just sort of try to get a feel of what is strength to weight of steel and strength to weight of RCC. So this is strength. The first number is strength. Second number is weight. So the strength to weight of steel is about 3185, and the strength to weight for RCC is 1600. Okay. Now please understand that these are just random numbers. Just to just to give us a sense of how strong is steel as compared to the other material. This does not have any physical meaning. This is just for our understanding, just like the example of Tanay and me lifting weights. Okay, so now you can imagine that steel has a very high strength to weight ratio than concrete. Now, perhaps now, can someone answer as to what does this mean? It's very simple. Don't think of it as a very difficult structural engineering question. So if one material has a better strength to weight ratio than the other material, what does that mean?
It can have a smaller cross.
It means that,
Take
sorry,
more. Sorry.
Please go on, no problem.
I was saying that it can have a smaller cross section, but it can take more weight. Like it can take more load.
Perfect. Very good answer. Can the other person please go on? Would you
or
like to add
even that
something?
you require less total weight. Yeah,
Exactly.
I was
Perfect.
gonna say that to support, like you need less weight of the material overall, so you save money if you're buying like by weight, as
Perfect.
long as
Perfect.
the price is
Very good
similar.
answer, both of you. What it necessarily means is that to take a certain amount of load, now you need lesser cross section, which means now you need lesser weight of the structural material, which means that overall your structure is lighter. So, when you compare apple to apple, just in terms of how much does the structural system weigh for a particular building, say you have a choice of constructing a building in steel and a building in concrete, everything remains same, okay, only the structural material varies. In that case, you can expect the structure that has steel to weigh lesser as compared to the structure that has concrete. And that helps us because naturally a lighter structure is going to need a lighter foundation. Lesser cross sections are going to give you more space to plan. They are going to optimize your FSI. Okay, so that I think this is a very important edge that steel has over reinforced concrete. Next, and that this is something that we have discussed at length, that it has a very high ductility. We've also discussed that ductility is nothing but the ability of a material to undergo deformation without rupture. Okay, and the stress strain curve gives a good understanding of how ductile a particular material is. So if I were to compare the various graphs that I've shown on the left figure, I think it is a no-brainer that the green curve, the material with the green curve, has the highest ductility, and the material with blue curve has the lowest ductility. So we already know a measure of ductility. Okay, and especially in seismic, response, this particular behavior is extremely important. We really do not want a material that has a very high strength but that fails suddenly. Instead, this now, for example, the red curve is a brittle response that it fails suddenly. It cannot take a lot of deformation. On the other hand, the material with the green curve, though it has the same amount of strength, but it has a lot of ductility. It can absorb a lot of energy. That is something that steel has, and that is something that we are going to capitalize on when we design steel, particularly for lateral loads. Now, just to give you a feel of how ductile steel is when we compare it with its peers. So this is mild steel, highly ductile. This is medium or high strength steel, has a higher strength but has a lesser ductility. And now let us compare it with our other favorite material, that is concrete. Let's just get a feel of how ductile steel is as compared to concrete, right? Either in terms of strength or in terms of ductility, whatever. It just apple to apple, it just outweighs concrete completely. Then the next one is elasticity. Now, when I start this course, I start with a certain assumption that perhaps this particular batch has sorry.
Hello. Sorry to interrupt. Can you go a little slow? It is a little difficult to catch up.
Okay, perfect. Do you want me to go back,
Sorry.
or do you just want to? Do you want me to go back
Can
and
you
repeat?
from ductility? Yeah, can you repeat from ductility, please?
Okay. So
Thank you.
yeah. So the next intrinsic property of steel is that it has high ductility, meaning that even after it cannot take any more load, but still it can deform significantly. Now let us go back to our bodybuilder Tanay. So even though he cannot lift more than 20 kgs, but he can do 60 reps. I, on the other hand, I can do 10, but I can do only 20 reps. So I'm neither as strong as Tanay nor as ductile as him, because even though he cannot increase his strength, but he can increase his reps. So it is that way. So tomorrow, if I build myself, if I look at him, I think if he can do it, I can do it. And I suddenly go and lift 30 kgs, and I can do 10 reps. So it is something like that. So he can do 20, but he can do 60 reps. If I lift 30, I can do 10 reps. So there's an increase in my strength. There's not increase in the repetition. So there's not increase in how much that particular exercise can last for. It is similar to this. So we are looking for a material that not only has good strength, but also has good ductility. And our stress strain curves gives us a sense of how ductile that particular material is. So if I look at the left figure, that I've sort of just given some random graphs that have of materials that have a certain strength and that have a certain ductility. So you don't know the number, but when you look at that graph, you can say that the green graph, or the material with the green graph, has the highest ductility, and the material with the blue graph has the highest strength. Okay, in a nutshell, the stress strain curve is a measure of the ductility of any material. And in earthquake response, we sort of want the material to behave ductile. We do not want a material that goes like the graph that is shown in red, because here once it has reached its strength, it cannot deform any further. We do not want a brittle response, we want a ductile response, and this is what steel has, and that is why this behavior is important to us. So
Bhargav, I think
yeah,
discussed this last class, but I just had one clarification.
go on.
So when we normally loads, we look at a ductile material as something we want to use for trusses and beams where we actually want to, put the material in high tension, right?
Okay.
I'm asking, is that
So
correct?
yeah, okay. So if I understand your question correctly, if
Yeah.
you're talking about ductility, we are particularly talking about certain members that we want to behave in a ductile manner, right? Is that your question?
Yeah.
Okay.
Yeah. So we want whenever there's an object in tension, we consider something very ductile, right?
It's not that whenever something is in tension, we consider it to be highly ductile, because ductility has, okay. So let me first try to answer your question, and perhaps then, discuss it further if you still have any confusion. So we look at ductility from an element level and from a structure level as well. Okay. So if your elements are ductile and you connect them in such a way that the connections are also ductile, then your entire structure is going to have a ductile response. Okay. So it's not like we are going to need ductile material only where we have tension, because earthquake is all about stress reversals. Okay, these concepts might be new to you, but just try to understand the crisp of what I'm saying. Earthquake induces all forms of stresses in members, so uh, it's not necessarily that we sort of go with a ductile member only at the locations where we uh, expect or anticipate tension, and we don't sort of differentiate into members that need a ductile behavior and that do not need a ductile behavior, because every member does, every connection does, and that's how the entire structure becomes gives a ductile response. So the bottom line is we really don't categorize as to which members need to be ductile. I'm talking about structural system only, the main lateral load resistance system and nothing else. Okay, so my beams have to be ductile. My column, if you are at all designing it for a special detailing, then every element of it needs to be detailed in such a way that it is ductile. Did I answer your question?
Yes, yes. I had another one, but this answers that as well.
Okay, perfect. So this graph is just a representation of how ductile is steel as compared to concrete, and how ductile mild steel as compared to medium and high strength. This is just a representation. Okay, we're not putting any numbers to that because as architects, we're not expected to remember numbers, but just get a feel of what.
Bhargav?
Yes, please go on.
Yeah, I just want to ask that the range of ductility for a material in a stress versus strain graph is considered till its fracture point, right?
Yes.
The area it covers under till its fracture.
Yes. Yes.
Thank you.
So normally it is considered from the point at which it starts behaving in a plastic manner till the material fractures. So that sort of is a measure of how ductile that material is. Now the third point is elasticity. The example that I was trying to put is that when I start this course, I start with a certain assumption that this particular batch is very good. They keep asking questions, they keep answering questions. So they have a very good fundamental base on which I can build on the design of steel and concrete. That is a fundamental. See, that is an assumption that I start with. But I do not get a consistent response to come to this conclusion. So in some lectures, you're doing really great. That there are questions coming up. There are very good answers coming up. Very good questions coming up, and that's how I see that. Okay, we are really building up a good course. But in some other other lecture, perhaps you have put an all nighter, and you're really not into in a mindset of studying this subject, and then there's no consistent behavior. So this inconsistent behavior sort of makes it difficult for me to understand as to how to structure a course in such a way that there's always a consistency, and that confuses me, and I cannot predict a behavior. But if there's consistency in terms of what I put in on the table, what you put in, and we could really build up something, then I have a good idea of how you are going to behave to this particular course. There's a similar situation with steel and concrete. Steel, you saw that irrespective of what the grade of steel is, irrespective of where you test it, irrespective of which machine you use to test it, there's always this linear portion that remains same. And that gives you a good understanding of how steel is going to behave. And that gives designer very good advantage because you can predict how it is going to behave. Okay, so elasticity is a very important property because this gives me as a designer a very good idea of how it is going to behave, right? On the other hand, concrete, but we'll study this in the next course, but just to give you some start, concrete on the other hand does not have a constant modulus of elasticity. Forget about different grades. If I take one particular grade, concrete does not have a constant value of E at any point. The value is constantly changing. I'll just go back to this curve. I know this is not a perfect representation, but the entire curve is it's sort of parabolic. There is no linear portion in it, meaning that the modulus of elasticity keeps on changing as you load it. Now, if you take a different strength of concrete, and if you do it, you will get different type of curve. So what it means is I really cannot guarantee how concrete will behave because its E value is constantly changing. Okay, so that's a very important add-on that steel has. That it's you can predict its behavior. It has elasticity, and the number is constant irrespective of what grade of steel you use. So that helps us design better structures. So a quick question for you. So I have 4 materials and I've provided the moduli of elasticity for all the materials. The question is, arrange in decreasing order of elasticity. Fastest finger first, come on.
Steel is the most elastic, I'm guessing.
Okay.
Then the rubber band.
Okay.
Then concrete and then diamond.
Okay.
I'm not looking at the numbers here. Was it supposed to be?
Yeah. So this is based on a pure, logic that, okay, I think logically this should be more elastic than this, and okay, I get it. Any more answers?
If you
and
look at, sorry.
I think diamond has the most,
Okay.
then steel, then concrete, and then the rubber.
So I
Because
think
higher,
go on.
because higher the value of Young's modulus, higher will be the elasticity.
Okay. So he's basing his conclusion on the values of E, and he thinks that the larger the value of E, the higher is the elasticity. Any more thoughts on this?
Yeah,
I think it should be the other way around.
Okay. So she thinks that it should be rubber and then concrete and then steel and then diamond, right? Decreasing order of elasticity.
I think it should be in decreasing, it should be diamond, then concrete, then steel, then rubber band.
Do you mean to say that diamond is the most elastic or rubber is?
No, rubber.
Rubber is not. Okay, perfect. So I think we have, we have all the ways of looking at it, and now let us see what is exactly correct. So, unfortunately, the common sense understanding of elasticity is not the definition of elasticity in physics. Physics says that the harder it is to strain a particular material, the more elastic it is, because it is a ratio of stress upon strain. So, smaller the value of strain, larger is the value of elasticity. Smaller the numerator, greater is going to be the number. So, it is most difficult to deform diamond. Therefore, the strain value is very small. Therefore, the elasticity is very large. Okay, and a common understanding कि या भाई खींच लिया तो elastic. So that's fine. That's common understanding. There's no wrong with it. But when we are dealing with structural engineering or physics, there elasticity has been defined in such a way that higher the value of E, higher is the elasticity. Okay. And
But won't diamond and concrete shatter before deforming? That's why they don't deform.
no, that's a different story. We're not getting into behavior. We are just trying to understand how much stress is required to deform it by a unit amount. Okay, we are not getting into a ductile or brittle behavior.
Right.
Another important property is that it is sustainable and energy efficient because it can be recycled infinite number of, I mean, not practically but theoretically it can be recycled infinite number of times, and that is what is actually done. Nearly 50% of the steel that is produced every year is recycled. Now, what difference does it make if the steel is from new or virgin materials or recycled? Now, if it is recycled, then it uses about 1/3 of the energy that is necessary for steel from virgin materials. So basically what you're doing is you're using less energy for producing the same component. And hence, lesser amount of energy is going into that building. And therefore, in that terms, it is very sustainable and energy efficient. Another thing is you can just, if you decide that now the operation of this particular building is over, you can just dismantle it and you can use the same steel section somewhere else with little or no treatment, depending upon what is the, status quo of that member. So in that way, it is highly energy efficient and it is very sustainable. Then there are some things that really give it an edge over RCC. Number one is prefabrication. So steel is produced, it is manufactured and assembled under very controlled conditions of the factory, and therefore you can expect the member to have a superior quality. On the other hand, more than 80% of the concrete that is normally used is cast in site, where there is very little or no control over the quality. Okay, so that is definitely an advantage that steel has. So all the components that are already cast in the factory need just to be transported to the site and lifted and connected to the other members by bolting or welding, whatever. So because of this, you can really plan your activities in a better manner. there is very less site preparation that is required, because unlike concrete, for concrete you have to have space for all the materials. Then you have to have a certain mechanism for preparing concrete in very huge sites. It is not uncommon today's. It is not uncommon these days to see a ready-mix concrete plant on the site itself. So there's a lot of site preparation that is required. But for steel, it's not the case. Then when you will actually come into the industry, you will I'm sure you'll experience that it's all about how much cost you can save. Your solutions, the first thing is your solution has to be cost effective. So when we are looking at speed, steel is definitely much faster than concrete, because as we saw before, there's no preparation time on site. You just bring it and erect it. So what you're doing is basically you're reducing the time that a labor has to spend on site, and therefore you're reducing labor cost. Then there's almost no site fabrication required, which is not the case in case of concrete. And you can use it immediately after erecting it. For concrete, you might have to wait for some time until concrete has gained its strength. You can remove the formwork. Concrete has sort of achieved its 28-day strength. So there's always some time. So there's some lag that is required between concrete, between when you erect a concrete structure and when you can use it. But that is not the case with steel. It's ready, plug and play. You just plug it and play it. There's no follow-on trade accessibility. So the question is, how fast? I mean, what do you think? If I have to build, say, a 50-story building with steel, what is the least amount of time that I can take? Of course, you just theoretically you can just say 1 day, and just apply some logic. Perhaps think of what is the status of the industry today, and then just give me a number as to how fast can we build given what we have today.
A month or two.
A month or two, okay. That seems reasonable. Any more inputs? Bolo bhai, this is your class. Just speak up. This is your course.
I watch these YouTube videos where China constructs them in a day or two.
Yeah,
So
in a day or two. Okay.
I
I
would go
think
that extreme.
you
Or
would do
like
it.
20 days, maybe like 2 to 20.
Okay, I think.
With COVID prefabricated hospitals, we saw that they were built in around like I think 20 days.
Yeah. Perfect. So she has given a very good input, and we are going to see a very similar example from the same country, in which they constructed a 57-story building in mere 19 working days. So let's see what they've got. Just a moment. Can you hear the voice? Can you hear some-
It's not clear.
Just a moment. Okay, any thoughts on that? Okay, let me ask some specific questions then. So, yeah,
Sharing because
Yeah, we didn't see the video.
serious?
no, you're not sharing your screen.
Oh man. So could you not even listen to what happened?
No.
No, nothing.
Oh my, this is waste of quite some time. Now can you do it? Can you see?
Yeah.
Yeah.
Now any thoughts or questions?
I noticed that all of the columns are also. My voice is echoing, right?
No, it's good.
Okay. I noticed that all of the columns are also made of steel.
Yes.
But then it would be like super expensive to make all of the columns of steel too, because I mean I just assume that columns are much more heavy and it's very expensive to like construct them in steel.
So, when we take this decision to construct a structure in steel, then it's okay. Composite is a different ball game, but I'm talking in general. When we are actually designing a steel structure, so it's entirely steel. The beams, the deck, the columns, it's all steel. So it's not very uncommon to have steel columns. Now, there's always an option to have steel in beams and deck, and then design the columns as composite. There's this option, but if it's a steel building, it's entirely steel, so it's not very uncommon.
But would that increase the cost of the building a lot to have columns in completely steel?
It depends on what do you want to save your cost. So against that, what are you saving your cost on? Now, if you're getting a larger floor space, if you're getting a lighter foundation, if that steel, if it improves the overall behavior of the structure, and overall it is proving to give you a lesser number in terms of cost or time as compared to concrete, then it's a decision that involves all these studies. But we cannot just say if you're using steel in columns and it is an expensive structure. I think it's not how we can put it.
Okay, thank you.
Yeah. Come on, guys, we don't have all day.
Sorry.
Yeah.
I had a question because we discussed this earlier in class. So, what exactly is the main reason we don't use this in India? One is the reason that the time constraint isn't really that much. Like, we don't really need to construct buildings that fast because the building industry doesn't work in that kind of time frame, right?
Yeah. Okay, let us
But
try
is there
to
any other specific reason that large scale steel?
yes, let's try to answer your question in the next few slides. Uh, so perhaps I was expecting this question, but nonetheless, the reason that they were able to build it in 19 working days because there were about 4 to 5 months of preparation before they actually came on site. You know, the sort of fabrication, the level of fabrication that they were expecting took about 4 to 5 months. That's the first thing. Second thing is that everything was more or less uniform. There was not really a lot of space for customization. And I think as architects, perhaps you really don't want those kind of constraints wherein, you know, everything is just, you know, dabba dabba. You want to do something different, you know, you want your structure to look better. So, you know, does not necessarily mean that, you know, everything was done in 19 days. There was a lot of planning that went into it. And, you know, there was this uniform sort of an architecture that they could achieve. So these are perhaps some of the shortcomings that, you know, building fast does not always mean that, you know, we're building the perfect structure. Then the next property that steel has it can span longer because you can, you know, there's a variety of beams that you can use with steel. So you can use a normal I section, you can use castellated beam, or you can use a composite beam, or you can use a truss. By, you know, varying these types of members, you can really span long. But you don't have that scope for innovation in reinforced concrete. Okay, you can there's only a rectangle that you can use, nothing more. You can pre-stress it, but that's, you know, that's a different ball game. But if you compare only structural steel with structural concrete, you have a lot of space for innovation. You have a lot of space for trying out different systems, and thereby a space for, you know, spanning longer. That does not happen with RCC. Normally, okay, there are exceptional situations, but normally the maximum span that you can achieve with RCC is about 8 to 12 meters. But with steel, you can easily span somewhere between 13 to 20 meters and even more. There are spans about 30 meters using heavy trusses and so on. And this is particularly important in industrial structures because you really want a very big column free space. Also important in commercial buildings, office buildings, wherein you really don't want those columns to coming up. You want to maximize on the space that you've got. And the last is that it has standard steel sections. There's a huge catalog of different types of sections from which you can choose which section you want to use. So, you know, there's already some, you know, sense of reference. There's always a reference that you can have. And, you know, there's a combination of sections that you can try out to build what you want. Reinforced concrete, it is not that way. There's no fixed shape that you can give it, you know, give to that. It has its own advantages and disadvantages. But the point here is that there are standard sections. So you always have a reference when you are trying to, you know, fit something in. You have a sense of what types of sections are available. Even in a particular type of section, which of them are actually manufactured and which are not. So, you know, this sort of gives us a choice. So, do you guys need a small break or should we continue? Am I audible?
I had a question actually.
Okay.
When you said that it took like 90 days to complete the construction and 4 to 5 months for preparations like the prefabrication and all, why is
Yeah.
that not considered in the process as well, like in the time span?
Because what they are saying is they are calculating the time to build it. They're not, you know, really counting the time to prepare it. This is on site. We spent only 19 days. That's what they're saying.
But like logically, that comes under the process of the whole time span of.
Yes, it does. But uh, they are talking about the reduction in cost in terms of what time and money spent on site. So it's really not a, you know, apple to apple comparison, as in, you know, I took 5 years for reinforced concrete building, I took 20 days. It's we cannot compare it that way. Now, if you compare I broke the ground for a reinforced concrete building on day 1 and I took, you say, day 500 to complete it. In that terms, you can compare. They broke the ground on day 1 and they completed on day 19. But of course, there's so much preparation and planning that goes in. but most of the cost and most of the cost is spent on actual construction, and I think that is a sort of comparison that they're looking for.
Okay.
Hi, I have a question.
Yeah.
Uh, but isn't the cost for maintenance higher for steel structure?
Okay. Again, not necessarily. It is a general perception, yes, that and also that is what we have experienced on one of our projects, that the structure with steel turned out to be expensive as compared to concrete. Uh, but again, it depends upon a number of factors. Some of them being, okay, if you're using steel, how much are you really saving on space? Because with steel you can go for lighter sections, therefore there's an increase in the effective floor area that you can use. So what is the cost of the floor area that you are saving? So does that cost make up for the extra amount of money that you're going to put in erecting a steel structure? And so from a structural engineering point of view, which type of system has a better behavior? So it is based on a number of factors. Uh, so it's a complete study that we do. For example, we had a project recently wherein the client really wanted, uh, you know, he was very ambitious and he wanted that his tower should be the most beautiful tower in the city, and the mall that was beneath it should be the most beautiful mall in the city. And that naturally came up, that perhaps got the architects thinking, and they came up with a very beautiful design. But everything comes at a cost. So the initial design that they gave us included steel. Then we design the entire structure in steel, not as in design. We just the concept design and schematic design in steel, and that option was turning out to be extremely expensive. Then we studied the same in composite and in concrete, and finally the client chose to go with concrete. The reason was that there are all the factors that I mentioned. The client did all this study, and really do a comparison, as in how much am I saving if I'm saving on space, compare it against the extra cost that I'm putting it. If it matches, then fine. If it doesn't, then there's no point in going with steel, only because it is going to make your building slightly better than what concrete would do. So number of factors, definitely. But if I have to just answer yes or no, perhaps in most of the cases, yes, the steel structure might be a little more expensive than a concrete structure. But again, this is not universal truth. It is based on a number of factors. Any more questions? Okay, perfect. So I take this silence as no break required, and I'm going forward. So obviously, nothing comes without its limitations. Similarly, steel has its own set of limitations, very significant in some cases. It all depends on where you have to use it. Okay, the first and the most important limitation, or the most if sort of the limitation that gives it a lot of disadvantage, is that steel corrodes. Corrosion meaning that the corrosion is going to start eating off material from the section, and therefore the sectional area is going to reduce. So naturally, whatever is the axial strength, bending strength, compressive strength, that is going to reduce. And not only that, but it also reduces the ductility of that particular member. So the entire point of using steel is that we're using lighter sections, and if it's going to start corroding, it is going to start eating up the section, and hence the capacity of the member is going to be reduced, and the capacity of the structure as a whole is going to be reduced. So especially in cities that are especially in coastal cities like Mumbai, if at all there is a steel structure, it is going to need a lot of proactive care. There has to be a team that looks after that structure every in a pre-decided period of time. Now we have a number of steel bridges that are built by Indian Railways. A lot of bridges for crossing vehicles or pedestrian bridges. But you notice that those bridges always need a lot of proactive care. If they keep on painting it every now and then, they keep on making sure that it is not it is not corroded. So the bottom line is, it is a high maintenance thing, boss. If you want to build it and then just forget it, then steel is really not your thing. It will need care. It will need pampering. And steel is susceptible to damage due to fire. It's a very important thing. Reinforced concrete and masonry, inherently they have a very good resistance to fire. Steel, on the other hand, now does this not mean that steel is combustible? It does not start burning, okay? But it is a good conductor of heat. And whenever there's a fire in a particular section of a building, steel is going to conduct that heat to other section. And there's a chance that because of that heat that steel is generating, even the other sections of the building might start, might catch fire. And not only that, what happens is when the temperature increases, steel sort of starts losing its strength. So to give you a reasonable number, it loses about 50% of its strength at about 540 or 550 degrees centigrade, and these temperatures are very common in fires. So if it is losing its strength, naturally it is gonna come down. The members are gonna come down, and if it is not stopped, the entire structure might just come down. So this steel really needs pre-treatment when it comes to fire protection, and it might even happen that if you're using steel in your structure, you have to compulsory there's a compulsion to provide a sprinkler system. So it depends upon the bylaws of the areas, but long story short, if you're using it, you have to take care of its treatment for fire. There's a saying by Chuck Norris that men are like steel. When they lose their temper, they lose their worth. So that's how steel works. Again, a small video.
September 11, 2001. Hours after the Twin Towers in Manhattan come down, 7 World Trade Center collapses. Unlike the towers, it was not struck by an airliner. How could this possibly happen? This video explains how Building 7 collapsed due to uncontrolled fires, and also why the pictures fool so many people into believing that it was a controlled demolition. The collapse of the North Tower, only 120 yards away, ejected burning debris, some of which ignited office contents in Building 7. The collapse also damaged the water main feeding Building 7's automatic sprinkler system. And since most firefighting resources were diverted elsewhere on that day, firefighters decided to pull out of Building 7 and let it burn. Fires moved through, burning uncontrolled for nearly 7 hours. At one point, firefighters measured a bulge forming in the southwest corner and determined that Building 7 was at risk of collapsing. How could a skyscraper bulge and then collapse due to a fire? The construction method explains how it happened. 7 World Trade Center and the Twin Towers were steel-framed buildings. In some skyscrapers, the structural support is concrete, or it can be a combination of concrete and steel. In 2001, the complete collapse of a tall steel building due to fire was new. However, in January 2017, a steel-framed high-rise in Tehran caught fire, and it, too, collapsed to the ground. And in 2005, Windsor Tower in Madrid, which was framed in both steel and concrete, caught on fire, and parts of it collapsed. Which parts? The upper steel portions. The building's concrete core and massive concrete sections called transfer floors survived. None of the 3 World Trade Center buildings had these concrete structures. The Tehran and Madrid fires prove that fire can destroy steel construction. When London's Grenfell Tower experienced a long and intense fire in 2017 without collapsing, it gave 9/11 conspiracy believers a new talking point. What was the difference? Grenfell Tower was a concrete building, not steel or even a combination. The construction is critically important to a building's performance in a long fire. So this comparison is entirely misleading. In long fires, steel weakens considerably. It also expands, and if this expansion is uneven, connections can break and failures can occur. This is why steel buildings incorporate fire protection insulation to delay these dangerous conditions. But no one anticipated the duration of Building 7's fires or the lack of water that would have helped to control them. Still, questions remain. Why did it collapse in such a seemingly symmetrical, uniform manner? This is undoubtedly the most misunderstood aspect of this engineering disaster. The World Trade Center buildings were a specific type of steel design, called tube frame construction. In a tube frame design, most of the support columns are on the perimeter to allow for large, open floor spaces. These columns are then rigidly tied together, creating a shell or exoskeleton, the strongest part of the building. Critically, this exoskeleton is braced and stabilized by the structure of each floor. The agency that investigated Building 7 believes that an internal failure occurred at a particularly vulnerable location, which led to a collapse of the internal structure that progressed vertically and then from east to west. This is consistent with a video taken by CBS News. Penthouse structures can be seen collapsing, first on the east side, as the interior caves in underneath. Daylight is visible through windows. Some 8 seconds after this internal east to west collapse begins, the massive exoskeleton is left hollowed out, like a giant empty soda can. With no bracing to stabilize it, the exoskeleton buckles under its own weight and disintegrates near the base, and the last part of the structure comes down very fast. That's precisely what tricks people into believing that Building 7 and even the Twin Towers were demolished. The rigid, visible exterior holds together as it comes down. This superficially resembles the way old buildings look when they're imploded, except, of course, for the extremely loud detonations immediately prior to the collapse. Also, parts of 7 World Trade Center landed on buildings across a 4-lane street. For a supposedly controlled demolition, the collapse wasn't very controlled.
Okay, so as a result of this, and as a result of what you experienced in the past, now it's almost compulsory to provide steel with fireproofing. There are a number of ways of doing it. We're not going to get into that, but the bottom line is, if you're using a steel building, also consider the cost of fireproofing. Fireproofing during constructing the building and even after, for example, the sprinkler systems and so on. And last but not the least, cost implications. Obviously, more time and expertise is required to design connections. Then the drawings are relatively more complicated. There's this shop drawings that need to be done. Then also on site you require skilled workforce, fabrication and erection. So therefore, in general, you can see that the cost is relatively high as compared to RCC. Okay, any questions there?
Can you go a little slow? It's very difficult to take notes.
Okay, I will try to. Okay. I'll
Can
go
you
ahead.
repeat the cost part? That's like.
Yeah. So you also have to spend, more time and expertise on designing the, members as well as the connections. And on the top of that, you need skilled workforce for fabrication and erection. It is not like concrete where you can work with skilled workers. So anyone who who's going to erect it has to be an expert in that. So naturally, the labor costs are high, and on the basis of everything together, we can say that in general, the cost of structural steel is slightly higher as compared to that of reinforced concrete. And that is perhaps the reason why, and along with other limitations that steel brings in, that is the reason why we do not see a lot of steel structures commonly, especially in India. Okay, can we move on?
Is the fireproofing done on the site or in the factory itself?
Now, for the structures that I've seen, it has been done on the site, and mostly it has been number one, which is sprayed cementitious or gypsum-based coatings. And you also saw it in the video, the guy spraying this cementitious materials on the elements. So it has to be done on site because the members are to be connected to each other, and after they are connected to each other, we can do this.
Okay, thank you.
Yeah. Okay, last, part of our introduction is the standard steel sections. I mean, what are the commonly steel sections that you should know and, start with in case you're working with a steel project. Now, they can be categorized into 4 types depending upon how they're manufactured and, what type of sections are they. So it's flat hot rolled products. So hot rolling is a way of manufacturing the, steel components. Then there are hot rolled sections. Then our connections consist of bolts and welding electrodes. And finally, there's this cold rolling is another way of manufacturing these elements. We are particularly going to look at the first 2 types. Because, that is we are going to design our elements with these types of components. So flat hot rolled products, the family of these consists of plates which are thin but not very, but wide, thin but wide. Then there are strips which are extremely thin and wide. Then there are sheets which are corrugated. And finally, there are flat bars which are thin but very narrow. Then under the category of hot rolled sections, the most commonly used section is an I section, which is also called as a rolled beam. Now there are different types depending upon what is the aspect ratio of that beam. What is the width of the flange? What is the depth of the web? What is the relative ratio? So in general, just on the basis of the section and and the resulting weight. So I sections are categorized as Indian Standard Junior Beams, which is abbreviated as ISJB, Indian Standard Lightweight Beams, Medium Weight Beams, Wide Flange Beams, Heavyweight Beams, and so on. Now, you don't have to remember all this. This is just to give you a feel of what will you probably find in books when you start to go back and refer to what type of section I should use. You will perhaps find I sections categorized into these different types. The most commonly used type of an I section is Indian Standard Medium Weight Beam, which is ISMB number 3. So this is the most commonly used beam section. And if you are going to use an I section for a column, then the last 3, that is ISWB, ISHB, and ISSC. These are the most commonly used beams. These are the commonly used I sections for columns. The first 3 are used for beams. Amongst that, number 3 is most common. Then we have channel sections, and similar to the previous categorization, we have Indian Standard Junior Channel, Lightweight Channel, Medium Weight Channel, and Parallel Flange Channel. Again, there's only a difference of the aspect ratio and nothing else. Then we have angles. These are very important in any structure. You'll find angles in a lot of structures. So we have Indian Standard Equal Angle, meaning that both the legs are of same length, and then Indian Standard Unequal Angle, so different length. It's self-explanatory. Then we have T sections. So again, there's a normal T, deep leg T, slit lightweight T, slit medium weight T, and slit T from edge sections. That you take an edge section and you just cut it from the middle so that you can get 2 T sections. Not very commonly used. If at all a T section is required, normally 2 angle sections are combined to form a T section. Then rolled bars, again very specific applications, not very commonly used. So you can have an Indian standard round bar, or you can have an Indian standard square bar. So these are solid bars. And again, very famous, tubular sections. We will almost in, whenever there are very unique applications, unique architectural applications, you'll see tubular sections. They have a very good, resistance to buckling, meaning that they serve as very good column members. So where there's an axial compression, these members are the most effective ones. When we get into compression members, we look at that. But just to give you a start. Again, you have three categories: lightweight, medium weight, heavyweight, so on. Now, all this is fine. That okay, there are different types of sections, and I have a huge catalogs of thousands of sections. So the question is, how do I decide as an architect? How do I start with any particular section, and what are the factors that I should consider before choosing a particular section? So the simplest factors that you can start with is number one, what is the area of cross section? Number two, what is the section modulus? Hang in there, okay? We'll see what these means, but just hang in there. Number one is what is the cross section area? Number two is what is the section modulus? And number three is what is the radius of gyration? Heard of this term before? In school, radius of gyration. We look at what these means and what these signify. Just hold on that thought for a moment. Obviously, the other factor is availability of section. Now there are hazards of section that the code gives, but not everything is manufactured because not everything is used. So it is always best to talk to a manufacturer and try to understand what type of sections does he manufacture, and then sort of start you start really putting sections in drawings. Because if you start with some random section and tomorrow you learn that in an actual project, and tomorrow you learn that it is not manufactured commonly, so either you'll have to pay extra or you'll have to start from scratch, so you lose on a lot of time. So it's always good to have an understanding of what is available in the market and what is not available in the market. Then obviously ease of connection. To give you an example, tubular sections are very efficient, but it is very difficult to connect them. Now imagine connecting a tube section to an I section with bolts. It does not have a plane surface. Therefore, there's nothing that you can put on that surface and then bolt it. So whenever you're using tube sections, it sort of comes with a assumption that you're going to have to weld those. Okay, so it also depends on how easy it is to connect other members. And finally, application. So there's no point in using a section that is not really made for that particular type of a structure. So normally I sections are used for beams and columns. Channel sections are used for purlins and industrial buildings. Angles are most commonly used in trusses and towers. All the electricity transmission towers that you see, angle sections are extensively used there. And the hollow tubes are used in plane and space trusses, columns, and so on. So in a number of space trusses, especially if you go to structures like airports, it is very common to see hollow tubes as a part of their space structure, as their space trusses and columns as well. So these are the design considerations. Now let us try to understand what does this Z and R mean, and why should we really understand these two particular parameters. Now, a term that perhaps people from science, 11th, 12th science, or in school also, perhaps this term might not be new to you. The term called moment of inertia. Okay, moment of inertia. So when we are talking about objects, that is when we say mass moment of inertia. But when you are talking about sections, we say area moment of inertia. Mathematically speaking, moment of inertia is the second moment of area. Let us take one more step back. What is moment? So whenever there's a force and there's a lever arm, we call it as a moment. There are equal and opposite forces, and there's a gap in between, or there's a lever arm. We call it as a moment. So that is the first moment. Second moment means that you are multiplying that lever arm twice. That is called a second moment. Now, what does moment of area mean? So when you're doing it for an area and not a point object, that is called as a moment of area. Take the example of a circular section. You can assume the centroid, it's not to be assumed. The centroid is at the exact center, meaning that you can assume that the entire area is concentrated at the center, and then you can compute. You take a reference axis, you measure the distance between that section and the reference axis, and you multiply the distance twice to that area. The resulting term is called as second moment of area. Okay, that's fine. So this is just a basic understanding. We do not need it. We did not get into the technicals and the details of it. But the question is, why is this term important to us? Because moment of inertia is the measure of capacity of the cross section to resist bending. Higher the value of I, or the higher the value of moment of inertia, higher is the moment that that particular section can take. So if I have two sections, one has an I value of say 5,000, other has an I value of say 7,000. I don't need any calculations to understand which section is better in resisting bending. If it is my need, then I will go with a section that has a 7,000 value of I. So simple. You can just compare two sections based on their I value as to how much moment it can resist. Okay. Remember one thing: larger I, larger is the capacity to resist bending. So since inertia is the second moment of area, which means that it's really important that how much distance is between the reference axis and the area that we are talking about. So if I give you two options, one is an I section, another one is a circular section. Or let me put it this way. If I give you two options, one is an I section and another one is an H section. Both of them have the same cross-section area. The question is, which one of them would have a higher value of moment of inertia? Okay, let's make this simpler. If I have an I section placed this way, and if I have an I section which is placed this way, let's call this number 1, let's call this number 2. And if I'm measuring the moment of inertia about this axis, let us say Z. So which of the two sections would have a higher moment of inertia about this axis?
1,
Why?
because it has more material far from the axis.
Perfect answer. Because, see, it is a multiplication of area times distance square. So जिसका distance जितना ज़्यादा, उसका moment of inertia उतना ज़्यादा. In the first section, you have so much material that is at a larger distance from the axis, and therefore you have a better moment of inertia. Here, there is a majority of material that is not going to resist any bending because it is, along the neutral axis. There's only some amount of material that is, at an extreme distance, and therefore you can expect one to have a much larger moment capacity as compared to two. Okay. Now, does this also imply, or does this also, it's sort of an explanation to why our rectangular beams look like this and not like this? So whenever we start a beam, why do we say that, this is 300 and this is whatever 450? And why do we not do it other way, that I say this is 450 and this is 300? Why do we start with this?
Is it because of the structural depth that?
This is because from its neutral axis, I have a larger material at a higher distance. There is much larger material here. If I compare it here, this distance is small. Here, this distance is large. For the same section, if I'm only changing the configuration, I'm getting a better behavior. Then why not go with that? Now, if we are specifically talking about rectangle, the moment of inertia is v d cube by 12. You might, very likely remember as to what it was. But, just trust me on that. It is vd cube upon 12. So it is proportional to the third power of depth. So if you have a larger value of depth, you are significantly increase the value of I, and hence you are significantly increasing the value of moment that it can resist. That is the importance of I. Long story short, greater the value of I, greater is the value of moment of resistance. Now, I is a general measure. A more specific measure of the bending strength is Z, which is called as section modulus. Okay, and it is defined as Z is equal to I upon Y. Now let us understand what that means. So if this is my rectangular section, if I want to know the value of Z at this location, then this is my distance, which is d by 2. So Z is defined as I upon the distance from the neutral axis, which is d by 2. I is bd cube by 12, and then we have d by 2. So this is equal to bd square by 6. So this is the value of Z for a rectangular section. So I is a general measure of bending strength and Z is a specific measure of bending strength. You're not going to get into specifics. Just understand steel table देखा तो उसमें क्या होता है और किसका मतलब क्या होता है. That's it. Whenever you open a steel table, you will always see these two values, I or Z. Let's open one and see. Okay, so this is a steel table for an I section. जिसमें the cross section dimensions दिए हुए हैं, and you get this I and you get this Z. So these numbers sort of measure the bending strength of that particular section. So if you look at the first one, which is ISMB 100, it has a Z value of 5.16. If you have ISMB 125, it has a value of 11. You can just look at this number and say that ISMB 125 can resist larger moment as compared to ISMB 100. We'll get into what IMB 100 and that later. Just understand the significance of I and Z, that's it. So larger the value of Z, larger is the capacity to take moment. That's yeah.
If it is written ZY, that means the neutral axis is.
Sorry. Could you please repeat?
If it is written ZY, so the neutral axis is the Y axis.
Yes. Perfect. I show you that we'll get into steel table. We'll look at what all these terms mean. If they say ZX, meaning the bending is about Z axis. Okay. If they mean ZY, so bending is about Y axis. Now that's a good question, and let's extend this point a little further. You can see that ZX is much larger than ZY. Isn't this what we just saw? Okay, we just put it this and then we just put it in the other direction, and we sort of anticipated that this is going to give you a higher value of I than this. And this is what even this table says, that ZX is much higher than ZY, and therefore we place our steel sections like this and not like this. Okay, just a moment. And the last property that is of importance to us is the radius of gyration. Now, again, let us try to understand this with the help of a sketch. Now, what does radius of gyration mean? So, if I have a section, say a circular section, and it has a certain moment of inertia, okay, irrespective of the axis that you select, it is going to have the same moment of inertia. Now, what if I convert this into a small point such that it should have the same moment of inertia? Now, if you remember, this is equal to A into whatever is a lever arm, let us just call it distance, y square. Okay. Now I have to maintain this, and what I've done is I've converted this area into a point. So what should I do to maintain the value of I? The obvious answer is increase the value of y. Okay. So if this was my reference axis, I increased the value of y such that it gave me the same moment of inertia. Now the moment of inertia of this circle with respect to this axis is same as the moment of inertia of this point with respect to that axis. So this y is called as the radius of gyration. Okay, to put it in technical terms, so it represents the distance from a section centroid at which all of the area could be concentrated without having any effect on the moment of inertia. You just take the entire section, place it at such a distance that the moment of inertia remains the same. That distance is called as the radius of gyration. Okay, this is what we have already looked at in school, perhaps in junior college. So I'm not going to spend a lot of time on it. So now, what does that mean? So your moment of inertia is say A into r square. Now r is the radius of gyration. So naturally, r is equal to square root of I upon A, and that is what is shown. So moment of inertia, the radius of gyration about x-axis is square root of Ix upon A. About y-axis is square root of Iy upon A. Okay. Now this is the measure of distribution of cross-section around its centroidal axis. So higher the value of r, better is the distribution of the cross-section about the centroidal axis. The question is, why is it important to us? So radius of gyration is a measure of capacity of the section to resist buckling. Okay, we are looking at two things here. First is Z. Z is the measure of the capacity of the section to resist bending, which is related to beams. R is a measure of the capacity of a section to resist buckling, which is related to design of columns. So when we are designing beams, Z is important to us. When we are designing columns, R is important to us. Okay. Now let us again, put things, in terms of sections. So if I have, say, a hollow section, this is a hollow circular section, and of the same area, if I have a solid circular section. Now, which of them do you think are going to have a higher value of R?
The first one, because the distance is more.
The first one, right? See, for one reason, you can just look at it and you can just say the material is at a larger distance, so boss, it is going to have a higher value of R. Now, if you want to get into mathematics, or if you just want to get into equations, you can just say that since both of them have the same area, so A is equal to I into distance ka square. Okay, this is same for both of them. So higher the value of I, higher is the value of radius of gyration, right? And we've just looked at ki I is a measure of distribution of material about a particular section. This will have a higher value of I than this, and therefore this will have a higher value of R than this. Long story short, the objective is put the material as far as possible from the centroidal axis, or from the bending axis, or from the neutral axis. The farther the material, the better is going to be the section modulus, the better is going to be the radius of gyration, and hence you will need a what I can say, you will need a lighter material, you will need a lighter section. So if this is getting too much information, being bombarded at one time, just give it a pause and think of it like, so when I start design, what parameters do I require? Z and R. Z signifies the design of beams. R signifies the design of columns. So this is what that you're expected to remember. Rest everything is up to you. You want to look at it from a factual point of view or understanding point. The fact is, Z is a measure of the resistance of bending. R is a measure of resistance of buckling. So that's a fact. But this is something that you have to remember. But the rest is all a theory that you already know. What we have done in this lecture is we've just quickly brushed up that. A quick feedback. Are you guys there? Are you guys understanding what I'm trying to say, or is it very fast bouncer?
We're understanding, but yeah.
Should I take it as you're understanding everything or you're understanding nothing?
There's no specific doubts. I think I'll just have to watch the recording again to be clear with it once or twice. That's
Yes,
all.
and and do it. Nothing really goes in the first pass. But I'm not spending a lot of time on this because we have much important much important content to cover later on. So this is not really a part of syllabus that the university says that you have to cover. This is just because we are trying to build a foundation on which we can build our actual content. So I think it is not just enough to say that look at the steel table and just look at the Z value, and whatever Z value is greater, and then it has a better. You just understand why. So that's the story of how to select a section. Radius of gyration should be high if it's a column. Section modulus should be high if it's a beam. Okay, these are the basics. Now, obviously, there are much more details. It is not that easy. Much more details, but basics pata hai, so we can build on it. Now,
I have a question.
Yeah.
Might be a silly question, but like when you showed us the steel table,
Yeah.
in that it showed like for I, it showed values of like it showed two different columns for X and Y. Oh wait,
Yes.
sorry. It has same for R as well.
Yeah. There's going to be a radius of gyration for bending about X direction and for bending about Y direction. Okay. So now, just to understand which type of sections are which type of structures. I section used almost everywhere, particularly for beams and columns and bridge girders. In channels, very common in purlins. And if you walk around one of the train stations in Mumbai, you will also see column sections used as columns. Channel sections used as columns, but they have combined two channel sections to form a box section. So I don't want to get into the details of it, but if you happen to visit any station, perhaps you might just see one channel section like this, another like this, and then they just put a plate here so that both of them act together. So you can really use, this is not a composite section. We are talking about pure channel sections, and hence I've not included it in this example. The most common use is as purlins in the industrial building. Angles, again, very common. You can see it as the cord members in trusses and very extensively in all the transmission towers. Then hollow tubes, almost all the space trusses are made up of hollow tubes. A number of columns as well are made up of hollow tubes. The example that you see on the right. I think with this, I think it's enough an introduction to this course. I think we've not just introduced, you also learned about a lot of things that perhaps we did not know before, and revised a few things that we want to need further in our journey. So I get a sense that I've been really fast in this particular lecture, and as I said before, the reason being that this is really not our point of focus. This is just the ground that we require to build on. We have much serious matter to discuss in the coming lectures, and I want to spend time there. So how now so that does not justify me going fast, but how that can really help is that you read this again. And I had shared the presentation with you before. So if not, what is going to be taught further, at least read whatever has been already taught. If you read what is going to be taught further, that gives you an edge, and that gives you, that gives you a quicker understanding of whatever is being taught. So what I'll do is, I'll share the presentation that I'm going to discuss in the next lecture as well. Okay. And again, I'm going to spend the next lecture on building up the actual course. We are going to learn a very important topic named as limit states method of design. So we are going to learn about limit state philosophy. That is the basis for entire steel design that we currently practice and entire reinforced concrete design. So next class is also going to be building up basics, but basics that you have not learned before. It's going to be something new. So I really urge you to sort of, go through the presentation and come prepared for the next lecture. Now, since I told you before, next lecture there's going to be a quick quiz during the first 10 to 15 minutes, or we can schedule this in between, however time permits. So please come prepared. The way I conduct quizzes is that I just create a Google form, multiple choice questions, and then we get the statistics right then and there. So, our objective is to keep on improving statistics as we go ahead in the course. So please come prepared. Please at least read this presentation, if not the next one. But if you read both, then, you can be sure that, we'll be traveling at the same speed. I think that's enough from my side for today. If there are any questions, please shoot. Else, thank you very much for your patience and see you in the next class.
Hi, I had a question.
Go on.
So as we saw the example of the Windsor building in Madrid, Spain, which was part concrete and part steel, and since its core was concrete, so that did not collapse, but the facade damaged due to the fire. So
Yeah.
is there any scope of restoring that building since its core was standing right there? And so is there any scope of restoring the building?
I think it depends upon the extent of structural damage. So there cannot be a yes or no to this, because there really needs to be an assessment of, even though the concrete structure is standing, but how much has it been damaged? If it's significant, then if it is going to need a lot of retrofit, that is going to cost a lot of money. Then I think the evaluators might think that there's no point in restoring this, because the cost of retrofit itself is very high, and only frame is left. So frame, we can just demolish and build a new frame. That's not the point. But if the extent of the fire is small, it's local, there's no impact on the global behavior of the structure, then definitely perhaps we could think of restoring it and start utilizing it again.
All right. Okay.
Okay. Any more questions?
I just wanted to clarify on one thing. So when we apply the fire resisting coating, all it does, it prolongs the time for building to collapse, right? I mean,
yes.
It doesn't really safeguards or something. It just prolongs the time.
Yes, it just prolongs the time, and that gives us time to get out of the building. That's it. So,
Okay, yeah.
whenever we design anything from a fire resistance point of view, there's always this thing called as fire rating. So every member has its own fire rating. For example, let us consider a reinforced concrete building. The columns, the most important members, like the columns and the structural walls, they are required to have a fire rating of 2 to 4 hours, meaning that after fire starts, it should stand for at least 2 to 4 hours, whatever is the fire rating, say 3 hours. And then when we come down to other members, say beams or slabs, then they have a different fire rating, say 1 to 2 hours. So every element has a fire rating. So when you apply a coating on that, what it does is it improves the fire rating, meaning that it can stand longer. Does not necessarily mean that it is going to stand forever.
Yeah,
Also,
thank you.
does the fire resistant coating need to be reapplied like over time? Because I remember in the World Trade Center, what happened with a lot of New York skyscrapers was that the newer one, which was not asbestos based, kept falling off due to the pressure of people walking constantly and everything. So a lot of those buildings had damaged fireproofing. So do we need to now reapply it, or has technology improved enough that once it's applied during construction, it's enough?
I think if you can visually see that it is falling off, then there's no option but to replay again. But if I think it's a part of visual inspection. If if the fire expert says that that's enough, and there are no cracks, or there's no spalling at any location, then I don't think that it has to be reapplied. But if you see a visual damage, as you mentioned, it has to be done again.
And usually it doesn't fall off anymore, right? Like because that was when asbestos was just being phased out for not for non-asbestos based fireproofing.
Now,
So
not that
that's
I
why I
have
think that
heard
was
of,
the issue.
but I cannot say with confidence that it never needs to be replaced. There might be situations, but just not that I'm aware of.
All right, thank you.
Yeah. Any more questions? Perfect.
If you're using, sorry.
Yeah.
If you're
Yeah, go
using circular columns, you'll have to weld it, right? You'll have to weld the beams.
Yes, more like majority of the times, yes, because it does not provide a flat surface. You can really bolt something if you have flat surface. And another thing is, how will you access the other part of the bolt? If it's an I section, you can always drill a hole, place a bolt there, and you from the other side you can tighten the nut, right? Here, the other side is not accessible. It's inside that section, so there's question of accessibility, and for that reason, it has to be welded.
Okay, thank you.
Yeah. Okay, if there are no further questions, I think we are done for the day. Have a good week, have a good weekend, and see you on next Saturday, perhaps, with a better understanding of whatever we have learned so far. So goodbye, thank you, and take care.
Thank you.
Thank you.
Thank you.